Magnetic field force between two current carrying wires. Let's have two wires that are close to each other, separated by a distance d, and they both have current going from bottom to up. We'll call this guy here wire A and wire B. Now, each wire is going to create its own magnetic field. We've discussed that earlier. Now, if they each create their own magnetic field, there should be some interaction between these two wires, and that's what we're going to derive. So first, let's just look at wire A. Wire A generates a magnetic field, and here you see these loops because at every point on wire A you will have a magnetic field that circles around it, and you can use the right hand rule, the thumb rule. Put your thumb pointing up, curl your fingers, and you'll see that they're curling in a counterclockwise direction. Now, at every point here where wire B is, the magnetic field strength is mu0 times the current in I1 in wire A divided by 2 pi and the distance between the two wires, which is d. So this distance here, that's d. So let's just summarize what's happening here. I'm just worrying about the magnetic field that's created by wire 1 here, wire A, that current 2, which is going through wire B, feels. It is feeling this magnetic field. We have the same diagram from the preceding page where we have our two wires, wire A and wire B. Wire A is generating a magnetic field and wire B is within that magnetic field. So we had this equation earlier where the force on a current carrying wire that's in a magnetic field is IL times B. Now let's look at each one of these terms. First of all, the magnetic field over here is going into the page, so it's perpendicular at every point to wire B. So we want to find the force on wire 2. Okay, so first what we have is we need the value, the magnitude of I2. So you can see here that's I2. We have the length of I2, which is L. That's not on the diagram, but it's this distance from here to here. And the magnetic field due to wire A, which is B1. So note how we have I2, all right, because we want to find the force on wire 2, but it's in the magnetic field by current 1, so it's B1. Now, we found B1 from the previous slide. Okay, so let's go back there for a second. B1 is mu0 I1 over 2 pi d. We come back to our page and we plug that in for B1. So this term here came from the previous page. So I have I2, I have I1, I have L, I have the distance. I do a little rearranging of this equation to make it look prettier. I put the i's next to each other. And the force that wire A exerts on wire B due to its magnetic field is mu0 I1 times I2 times L divided by 2 pi d. Now I could do a similar analysis for the force that wire B over here exerts on wire A, in which case I would draw wire B's magnetic field, which would extend over here, and in this case it would be coming out of the page, and that's what wire I1 would feel. Or I could just take a shortcut. Newton's third law. Newton's third law doesn't just work for mechanics, it also works for electricity, it works for magnetism. So whatever force that wire A exerted on B, wire B must exert on wire A. So I'm just going to take that shortcut for now, and the force that each wire exerts on each other is mu0 I1 I2 times L over 2 pi d. Now that we've determined the magnetic fields and the force between the wires, at least the magnitude of them, let's see which direction they move. Okay, so I've actually got two setups here, and let me just separate them like this. So put this guy over here. And let's look at this case where I have two wires separated by a small distance d, and in this case I2 is going up, I1 is going down, so the currents are in opposite directions. Let's look at the magnetic field that I1 creates. If you put your thumb down, because the current in I1 is going down, you will find on this side it creates a magnetic field going into the page. So this is the magnetic field created by this wire, wire 1. So here's I2 in a magnetic field that's going out of the board, and the current is going this direction. So I use the right hand rule. I put my fingers, my 4 fingers, pointing up. I then, in this case, my palm is facing me because I'm going to curl my fingers towards me in the direction of B1, and you'll find that your thumb points to the right. So the force on I2 is to the right. Now let's look what's happening over here to wire 1. The magnetic field due to wire 2, see this B2 here, is coming out of the page. Because when you put your thumb in the direction of I2, curl your fingers around, you'll find over here it's coming out of the page. So this magnetic field is due to this wire here, wire 2. When I do the right hand rule, I put my 4 fingers pointed down, and in this case once again my palm is facing me. I curl my fingers towards me out of the page, and I find my thumb is pointing to the left. So right over here has a force going to the left. So what we have here is anti-parallel currents, or currents in the opposite directions, repel each other. Now you can look at when the 2 wires are in the same direction using a very exact same analysis, where I'll just do this one perhaps just a little quicker. I1 is generating a magnetic field over here that's into the board, which is B1. I now take I2 to find the force on it exerted by this magnetic field. I use the right hand rule, and I find that the force is to the left. I then look at I1. I2 will create a magnetic field B2 that's out of the page. So I1 is experiencing this magnetic field. I use the right hand rule, and I come up with the force to the right. So these 2 wires are attracting each other. So to summarize this right here, this is the most important thing on the page here, which is why it's in red. Parallel currents in the same direction will attract, and parallel currents in opposite directions will repel. And this is also observed experimentally.